Hello and welcome. Today we're going to talk about antiderivatives of complex functions and the fundamental theorem. So we all know the fundamental theorem of calculus of the form if f has an antiderivative, and we're going to call that capital F. So that we'll just put this in a real variable x, and that is we have f prime of x is equal to little f of x. Okay, so what are we going to do here? Then we know, this implies then that if I take an integral, I should say on what I'll call AB, then integral from AB of f of x dx is equal to the antiderivative evaluated at the endpoints. Okay, so with this result, it's pretty straightforward that the idea of integrating over an interval then is provided that on the domain of interest, this a to b, if an antiderivative exists for that whole domain, then if we evaluate the antiderivative at the boundary points, at the endpoints of our interval, and then take the difference, then we get the result, a way to compute an integral. And this is, of course, incredibly powerful. That's why they call it of course, the fundamental theorem of calculus. Okay, so what's going on here? And let's see if we can generalize that to that of a contour integral. So now we're going to talk about a contour integral. Okay, so we have z of t. Starting at a point, we'll call it A, and now this is going to be in the complex plane. We have some contour all the way to B, another number in the complex plane. So there's our complex plane. All right, so that defines our contour C. And we know then that we can write it as follows: f of z from, I should say that we can write this now that when we write this contour integral, we want to parameterize it so that z of t is equal to some function, x of t plus I y of t. Likewise, t runs from, we'll call it t1, all the way to t2. All right, and then when we want to write this complex integration, like so, we want to do this contour integral, we can rewrite that as integral from t1 to t2 of f of z of t times z prime of t dt, right? So this is now a constructive way to actually compute this integral, this contour integral here. So now let's talk about, now suppose that on the domain of definition, that means we have some sort of domain, we're called D, and our contour is completely inside of D. Suppose that on D there exists a function capital F of Z such that capital F prime, so F is analytic on this open domain, is equal to little f of Z. All right, so of course we can write this then. So I'm going to go rewrite this function then as, remember that this is just a complex. This integral reduces to two real integrals. So what we can do then is write this as follows: t1 to t2 of capital F of z of t times z prime of t dt. And of course, here we have that if I were to take d dt of f of z of t, that would be f prime of z times z prime. Okay, in which case I can rewrite this as integral t1 to t2 of d dt capital F of z of t dt. And of course, by the regular, normal, real-valued fundamental theorem of calculus, this is going to be this is going to be quite simply, we can write this again now as, we can think of f of z as equal to u plus iv, and capital F then of z as capital U plus I capital V, right? In which case we can write this as integral t1 to t2 of capital U plus, and then bring the, t2 of d dt capital U plus iv, these are capitals, dt, in which case we can write this as simply u plus iv evaluated at t1 to t2. All right, so I'm going to go to another page now and just restate our result, that if f prime equals f in the domain D where C is contained, okay, then we can write integral, the contour integral of f of z dz is equal to capital F at B minus capital F at A. Okay, again we have our contour like follows, where that's C, and there's some domain D where the contour is enclosed inside. And provided that this antiderivative exists, provided we can find this antiderivative, then now we have a really simple way of writing this. In fact, we can even state this as follows, where this is A and that's B, and those are complex numbers. We can write it now as follows. We can write integral from A to B, where those are complex numbers, of f of z dz. All right, so before we would use this contour, and what this really means is this independent of path. It doesn't depend on the exact path you take to get from one place or another. It only depends on the endpoints right there. Endpoints are all that matters. Okay, and that is precisely the result we get from the fundamental theorem of calculus in real variables. So the theorem that we're stating here is essentially just a rehash of the regular, normal, real-valued fundamental theorem. So let's of course go to example. We've already seen this, that of z to the negative 1. All right, if that's equal to our f of z, we know that capital F, the antiderivative, is just going to be z to the n over n. All right, because f prime of z is equal to n times z, or n times z to the n minus 1 over n. Those cancel, we get z to the n minus 1. Okay, in which case, if I take any contour, let's say we take a contour from, and we know this is analytic, entire, and so is capital F. Both capital F and lowercase f are both analytic entire, and the antiderivative holds on the entire plane. So if we can take a contour, let's say that we'll take a contour from, we'll just say negative I to 1 plus I. Okay, if that's a contour, then I can write that as like follows. So here's negative I, that point there, and then 1 plus I, right there, 1 plus I. So I can take any contour I like. I can take a jagged line getting there. I can take this line. I can take something like that. I can go around like this a few times and then eventually go in. I can do whatever I want. At any rate, I can write this down. Now let's try z to the third power to make our result complete. we can simply write this as integral c of z to the third power dz. We can now rewrite this as integral from I to 1 plus I. That's our new way of writing it. Now that we have an antiderivative that exists on the domain, to the third power dz, we can write that as z to the fourth all over 4 evaluated at I to 1 plus I. And so I'll leave that little calculation for you to do yourself. Now let's go over another example. Okay, let's go back to this. Now what about this contour integral z to the n minus 1 dz, where c is a closed path? I should have noted, actually, I'm sorry about this, that I should have noted that n could not equal 0 in all of the results that we just talked about. So we're going to continue with that. So let's talk about c being a closed path. So in the n equals not equal to 0 case, of course, we have capital F of z is going to be equal to z to the n over n. Okay. In the n equals 0 case, however, capital F of z is equal to log of z, right? Because we're saying that if f of z, in the n equals 0 case, f of z is equal to 1 over z. And of course, f prime is equal to 1 over z. But the problem with log is that we're going to, as I'll show later on, it doesn't have its domain is a bit restricted, as we know. Okay, so let's say we have a closed path in the plane. So we have some path, and we'll make it a positive orientation. So what can we say about this non-equal to 0 case? Well, we can write that down as we can start at any point A and then end at another point A, right? So we start at A, we go around, and we end back at A. And so we can say that's A to A of z to the n minus 1 dz. And of course, that's equal to z to the n over n, provided n is not equal to 0, and evaluated at A to A. And of course, the answer is f of A minus f of A, which is always 0. Okay, so so another conclusion we can make from this is the other thing we can conclude from this is functions with antiderivatives have or I should say, integrate to 1 on closed paths in their domain. Okay, so these are a bunch of observations. Now I want to collect all of them together and just state a very general theorem, and then we'll go talk about this in a little bit. Okay, so let's talk about what's the general theorem. So the general theorem is as follows. It's pretty straightforward. It's actually 3 statements together. So there's 3 statements. Three statements, all equivalent. And what I mean is, of our 3 statements, we have one statement 1, a statement 2, and a statement 3, and I'll get to exactly what they all are. But they all imply each other. That means if one is true, all is true. If one of them is discovered to be not true, then all are not true. Okay? So we can take them as equivalent statements. Okay, and the first statement then is, of course, that f has antiderivative capital F in some domain D. The second statement is that if C is any contour in D, so if starting at Z1 and going to Z2, then integral of f of z dz over that contour can be computed as the antiderivative z2 minus the antiderivative evaluated at z1. Okay, that's just our fundamental theorem of calculus. So that's nice. The next thing we want to do then is state the final result, which is closed path contours in D are all 0. Okay, so all of these are true, and we basically just stated that fact. We've kind of gone through examples of each of these facts. Okay, so of course the standard thing to do then is, number 3, in general, proving that any contour always nets out to be equal, any contour equals the difference of the antiderivative at the endpoints. Because C could be, there's infinitely many contours that start and end at these 2 points. In general, that's a very difficult thing to discover. Same thing here, that any closed path contour in D are all 0. That's a difficult thing to discover on your own, but discovering that a function has an antiderivative in f, that's something we can actually do. So in practice, of course, we discover or determine 1, and then we imply both 2 and 3. Okay, so really it reduces just determining 1. We want to discover we can find an antiderivative in D. And if we can, then we get 2 and 3 for free, which are, of course, it's a very powerful theorem. So the usual direction of implication goes from 1 to 2 and 3, and not the other way around. Okay, so let's now talk about another result. All right, now I'm going to talk about the case of f of z. So here's an example. Okay, f of z is equal to 1 over z. So this is, of course, the case of z to the n minus 1, where n is equal to 0. Okay, so this is that special case, right? So what's the domain here? The domain here is going to be the complex plane, but we're going to have to subtract the 0 point, right? So it's the complex plane minus that 1 point. So that's the domain. But now, what's the antiderivative? Antiderivative, of course, is log of z, because we know that log d dz of log is equal to 1 over z. Okay, but what's the domain of log? Well, the log, we have to choose a branch cut. So what's the branch cut? Well, we can choose it. We can take it to be anything we want. So in this case, we can choose it to be, let's say alpha is equal to pi. We'll take the standard branch cut, in which case complex log reduces to the principal value log, which we'll call the capital. Okay. So in this particular case, then, the domain is as follows. So in this case, the domain then is going to be the complex plane minus the points z such that y is equal to 0 and x is less than or equal to 0. Okay, so that's the, not less than or equal to, less than 0. So the so-called negative real axis. All right, so as long as our contour is inside of does not cross this point or does not go through that point, we're fine. So we can go any contour that stays within this domain is fine. So if I can do a closed contour there, like that, that's okay. I can go over here, that's okay. But whatever I do, I cannot cross over the negative real axis. All of a sudden we stray into a territory where the domain of our antiderivative is a region or a set of points in the plane that are not included in the domain of our antiderivative. So that is really the clincher here. So now let's talk about let's go actually compute an integral. So if I talk about a point, if I go from negative I plus 1 to I plus 1. Okay, so let's compute that one. So we can now put that in. So this is going to be 1 over z dz from 1 minus I to 1 plus I. Right, so that'll be the point here. It'll be right here. That's 1 minus I. Oops, mistake there. Okay, we can put that right here. That'll be 1 minus I right down here. I'm going to take that point and go up to 1 plus I. Okay? And so the antiderivative is, of course, log. We're going to use the principal value, though. We've chosen the principal value log of 1 plus I minus the principal valued log of 1 minus I. And let's see what that result will be. It's fairly straightforward. That's going to be natural log of root 2 plus I pi over 4 minus natural log of root 2 minus I pi over 4. Okay, we can see that these two will cancel because they're opposite signs. But likewise, we see we do get something here. We see we do get something here, which is we get I is equal to pi over 2. All right, so that looks like a nice result. However, we can't actually go all the way around and do any kind of closed contour that comes and would get close to that crossing point. So now let's just discuss what happens in that one particular case. So now let's take a contour, and we'll take the contour z of t is going to be e to the I t, and then t is going to go from negative pi plus epsilon to t negative pi, or sorry, positive pi minus epsilon, right? And so this contour will go like this. We're going to start right there and go around like that. And we're going to have a very tiny angle there of plus and minus epsilon inside there. Those two angles are plus and minus epsilon away from pi. And we're going to start there and move like that. Okay, so that means that we will now evaluate it as follows. So the integral on this contour of f of z dz, where this is going to be the integral of 1 over z, we're still working with that example. And that's going to be log at e to the I positive pi minus epsilon minus log at e to the I negative pi plus epsilon. Okay, all right. So So in this particular example, then we can easily see that this is going to be I pi minus epsilon minus I negative pi plus epsilon. And what we see here is we'll get 2 pi I, and then we have a minus I to epsilon. And we can see then that we have this 2 pi accumulation, where as we come closer and closer, if I get this contour to come closer and closer to that branch cut there from the top side, and I get this branch cut, or this side to come closer and closer to the branch cut from the bottom side, so as epsilon goes to 0, what we see then is that the result, integral of this closed path of 1 over z that encloses the origin, dz, is going to be equal to 2 pi I. And of course this is most certainly not 0. And that's because our function has, although we have continuity here, we can take the limit and get this result. The function itself is, the antiderivative of that function does not exist on the domain, over the complete domain in which the contour is taken, and so some sort of accumulated value comes out of this closed path integral that wouldn't have otherwise come out if we had a function with a derivative that an antiderivative that existed on the domain that the contour was on. All right. So with that, we'll talk later about how to prove this theorem. And so we've seen some important applications for it now. So thank you very much.